Okay, so in case of p-type semiconductors, so what are the majority charge carriers in case of p-type semiconductors? Holes. Holes are the majority charge carriers. Why holes are the majority charge carriers means here? So we are doping trivalent elements. Trivalent elements such as aluminum, gallium, indium. So we are doping here. So these trivalent elements. So these trivalent elements. So how many valence electrons these trivalent elements means? Only three valence electrons will be there. So but so these trivalent elements are covalent bond with four surrounding silicon atoms. Four surrounding silicon atoms. But these indium have only three electrons. So that's why so one electron is required to fulfill the bonding. One electron is required to fulfill the bond. So whatever the requirement of electrons in which at that place hole will be formed. Hole will be formed. Okay, like so hole will be formed. See here, indium needs one more electrons to complete its covalent bond. This electron may be supplied by the silicon subject to the either electron or thermal energy or optical energy, which will break the covalent bonds, thereby creating vacant electron site or hole on the semiconductor atom. Yeah, I will explain you. So see here, so this indium atom, here we are doping indium atom. This indium atom requires one hole. This this indium atom try to what is that capture the electron from the surrounding silicon atom. So how it will be captured means, if you supply the any electrical energy or thermal energy or optical energy to that material, what happen, this bond will be breaks, and this electron will supplies to the this indium atom. Here hole will be present here. So at which place hole, what is that electron breaks, at which place bond breaks, hole will be at that place. So what happened, hole will be formed. That's so like that situation. So this hole also, what happened, try to grasp the another electron. Okay, if you supply any external energy means, so this hole also attracts another electron, and so some another place hole will be formed. Like that holes will move entire the entire the p-type semiconductor. So that's why, due to motion of the holes, what happened here, so conduction will be takes place. Okay, yeah. Okay, so now see here. Mm. Now these holes, these excess holes. So these excess holes. So how many indium atoms we will dope, that much of holes will be formed. Those are all holes having particular energy. That energy level we will call it as acceptor energy level. Acceptor energy level. Each indium atom doping contains one excess of hole. So that those all holes combinedly form so one energy level. That energy level we will call it as acceptor energy level. That acceptor energy level is nearer to the valency band. Okay, so here this line represents the intrinsic Fermi level. That acceptor energy level will be below the intrinsic Fermi level and nearer to the valency band. Okay, now we will calculate the density of holes. In a p-type semiconductor, or carrier concentration of holes in a p-type semiconductor. Okay, now so this equation, density of holes in a valency band. So in case of intrinsic semiconductor, we calculate the density of holes in a valency band. Okay, that value equal P is equal to 2 into 2 pi mp star kt by h square whole power 3 by 2 into exponential of ev minus ef by kt. So this is the density level, density of holes in valency band. Okay, now we are calculating the density of holes in a p-type semiconductor. Okay, for that, the density of ionized acceptors. density of ionized acceptors. Here Na is the density of density of holes. Na is the density of holes in a acceptor level. Density of holes in a acceptor level, and F of EA is the probability of finding the hole. Probability of finding the hole. Okay, so we are finding the total density. Here holes will be present in the, so this acceptor level only. Holes will be present in the acceptor level only. Okay, that's why we are taking, so total density of holes in a acceptor level equal to, so Na into F of A. F of A. Okay, so here F of E value equal to 1 by 1 minus exponential of EF, EA minus EF by KT. EA minus EF by KT. Okay, so that is the F of EA value. See here. So I will show you that that equation. See that, yeah, so Na is, so F of Ea value, F of Ea is equal to 1 by 1 plus e power Ea minus Ef by Kt. So this is the F of Ea value. Okay, so here Na bar is the, so uh, ionized acceptor atoms. Okay, so that equal to Na into F of A. Okay, Na into F of A. F of A value is equal to 1 by 1 plus Ea minus Ef by Kt. Here Ea minus Ef. Ea minus Ef means, so energy gap between the, so acceptor and acceptor level and Fermi level. This value also very small. This value also, yeah, sorry, here energy gap between the acceptor and Fermi level is high compared to the KT. So that's why, so this value is very high. This value is very high means exponential value also very high. Okay, so that's why, so we can neglect the one here. We can neglect the one. Simply we can write, so this 1 by this value equal to e power so 1 by e power Ea minus Ef by Kt. Okay, if it will come to the numerator, so e power minus Ea minus Ef by Kt. Okay, so that only we wrote here. That only we wrote here. Yeah. See here, if you simplify it, so this will become, so F of E will become exponential of Ef minus Ea by Kt. Okay, so this is the, so F of A value. So this total Na into exponential of Ef minus Ea by Kt gives the density of ionized acceptors. Density of ionized acceptors. Okay, at very low temperatures. At very low temperature, the number of holes in the valency band must be equal to the number of ionized acceptors. Okay, at very low temperature. At very low temperature, so these uh, ionized acceptor atoms is equal to the, so density of holes in a valency band. Density of holes in a valency band. So that's why we are equating these two equations. We are equating similarly what we did in n-type semiconductor. That only we are doing here. That only we are doing here. Okay, see here. So now we are equating both equations. We are equating, so this equation and so this equation. If you equate both, because at low temperature, so density of holes in valency band equal to, so ionized acceptor atoms. Ionized acceptor atoms, that equal to, so we are equating both here. Okay, yeah, now we are apply the same logarithm both side. Now we will apply the logarithm both side. Okay, who is that every time? N not, so leave from the class. So why are you doing disturbance every time? If you do so next time means, so I will remove you from the class. Okay, so now here, so we are doing, so we are equating both equations here. We are equating both equations. So if you equate the both equation and simplify this equation, simplify, how to simplify means, so first we have to apply the logarithm both side. Logarithm both side. Okay, so simply how you will do means, this also, this total term also constant. Okay, because so 2 pi mp kt by h squared. So because we are maintaining constant temperature, the mp value also constant, h also constant, k is the Boltzmann constant also constant. So let us take, instead of this is, so this constant, let us take Na. Okay, so Na into exponential of EV minus EF by KT into, so here Na will be there. Na? Let's take here NV. Okay, NV. Okay, so if you will take NV means NV into exponential of EV minus EF by KT equal to Na into exponential of EF minus EA by KT. Okay, so if you apply log both sides, so then it will be easy. Then it will be easy. Otherwise, do directly. Otherwise, do directly. So whatever the easy you can do like that. Okay, so do yourself also. Do yourself also. Okay, now I am applying logarithm both sides. Logarithm both sides. So we know the formula. We know the formula of, so log a into b. Okay, so log a plus log b. Similarly here also log a plus log b. If you simplify it, so this is log of this total term plus, so log of exponential term. So log and exponential get cancelled, simply ev minus ef by kt. Similarly here also log na plus, so this log and exponential term gets cancelled, simply ef minus ea by kt. Okay, now so if you simplify, further simplify it, so what we will get? So EV minus EF by KT minus EF minus EA by KT. So that same terms I bring one side. So log terms one side and the remaining terms another side. Okay. Now, so this is, this side is log NA minus, so log of 2 into this total value. Okay. So now if you will write, so log A minus log B. Okay. How we can write? So log of A by B, log of a by b, na by this total term. Okay, now so this side, so kt is LCM, kt is LCM. If you simplify it, so minus 2ef plus ea plus ev. Okay, so send kt this side, send kt this side, and from this equation just we are calculating the ef. Okay, keep ef this side, send remaining other terms that side. Okay, finally we can get the, so this ef value equal to, ef is equal to ea plus ev by 2 minus kt by 2 into log of Na by, so this total term. Okay, now coming to the, yeah, so at 0 Kelvin. So at 0 Kelvin, say similarly, whatever we discussed previously, so at t equals 0, so we are keeping 0 here. So now F is equal to Ea plus Ev by 2. Ea plus Ev by 2. Okay, so at 0 Kelvin, what is the Fermi level in case of p-type semiconductor means? So that is exactly middle of the accepted energy level and valency band. Valency band, accepted energy level and valency band. That Fermi level is exactly middle of the accepted energy level and valency band. Okay, now this ef value, substitute this ef value in uh, this equation, this equation. Okay, this equation is the density of the holes in intrinsic semiconductor, density of the holes, density of the holes in a valency band of intrinsic semiconductor. Okay, so substitute that value, that ef value in this equation. Okay, if you substitute ef, that means only I am taking this term exponential of ev minus ef by kt. Okay, instead of ef I am substituting here. Okay, I am substituting, so above equation, this equation here. Okay, if you substitute and simplify it, yeah. Mm. So if you substitute it, we can get this equation, same whatever we previously discussed. And so here kt I am dividing individually, kt I am dividing individually. So kt gets cancelled here, 1 by 2 equal log of Na power 1 by 2 into, so here 1 by 2 equal log of Na power 1 by 2 into, so here some value will be there. So simply ev by, so here kt it will be. Okay, now if you solve these two equations further, if you solve these two equations, so we can get, so ev minus ea by 2 kt. So if you solve this last term and first term, so you can get ev minus ea by 2 kt. Okay, so and the remaining term will be log of Na by, so this total constant value, this total constant value. Okay, so finally if you simplify it, we can get exponential of ev minus ef by kt equal to, so this constant Na by, so Na power whole power 1 by 2 into this constant term into exponential of ev minus a by 2 kt. Okay, now substitute that value in this equation, that value in this equation we can get here. Okay, substitute, if you substitute that value in this equation, we can get the this equation, we can get the this equation. Okay, So if you simplify it, we can get P is equal to Na power 1 by 2 into this constant into exponential of EV minus EA by 2 kT. Okay, so some cases this constant value is just taken as NV. Okay, so this also become NV power 1 by 2. So previously we are taking total NV na, so here that is 3 by 2. Here into whole power 1 by 2 will be there. So that's why simply this equation we can write into, so root 2 into Na power 1 by 2 into Nv power 1 by 2 into exponentially Ev minus Ea by 2 kT. So this is about the density of holes in case of p-type semiconductor. Density of holes in case of p-type semiconductor, or carrier concentration of p-type semiconductor. Carrier concentration of p-type semiconductor. Okay, so here, so one more thing here, thus we find that the density of holes in valency band is proportional to the square root of the acceptor concentration. See here, so this density of holes is proportional to the square root of the acceptor concentration Na. Okay, if you increase the Na value also, what happen? Density of holes will be increases. Density of holes will be increases. Okay, this also proportional to the temperature also. This also proportional to the temperature. P proportional to the, so T power 3 by 4. P proportional to the T power 3 by 4. If you increase the temperature also, density of holes will be increases. Okay. Now we will calculate the variation of Fermi level F with respect to the temperature and acceptor concentration in p-type semiconductor. Okay, yeah. So as the temperature increases, the Fermi level F slightly drops towards valency band. So observe here. So as temperature increases, the Fermi level F slightly drops towards the valency band. Okay, and for further increase of high temperatures, the electron concentration also increases with respect to the hole concentration. Hence a conduction is reached such that N equal P. That means it becomes an intrinsic or pure semiconductor. Hence the Fermi level increases and reaches to the intrinsic level EI as case of pure semiconductor. Okay, this shown in figure. See here. So in case of initially at lower temperature, that means if you will take it 0 Kelvin, if you will take it 0 Kelvin, so the Fermi level is exactly middle between the acceptor energy levels and valency band, valency energy level. Okay, at 0 Kelvin. If you increase the temperature, if you increase the small temperature, what happen? So this will, that Fermi level shifts, that means decreases slightly. That Fermi level decreases slightly to the valency band. The Fermi level decreases slightly to the valency band. If you increase the further temperature, what happens? This Fermi level will be increases. That Fermi level will be increases and reaches to the Fermi level of intrinsic semiconductor. Fermi level of intrinsic semiconductor. What is the reason? Means if you increase the temperature, so that covalent bonds of a semiconductor will be breaks and the number of electrons will be increases. Number of electrons will be increases. Those electrons reaches to the conduction band. Those electrons reaches to the conduction band at very high temperatures. At very high temperatures, what happened? So electrons, number of electrons in conduction band equal to the number of holes. So that's why, so Fermi level also it will become like a intrinsic semiconductor. It will become at high temperature, it will act as a intrinsic semiconductor. That's why, so that Fermi level will reaches to the intrinsic Fermi level. Intrinsic Fermi level. So this is about the Fermi level in case of intrinsic semiconductor. Intrinsic semiconductor. Okay. So and once again I will revise you. So just simply what is the steps we are taking here. Okay, first of all, so in case of extrinsic semiconductor, so we are taking here p-type extrinsic semiconductor. In case of p-type extrinsic semiconductor, so majority charge carriers are the holes. So these excess holes combinedly form one energy level. That energy level we will call it as acceptor energy level. acceptor energy level. Okay, so that acceptor energy level will be just nearer to the valency band. That accepted energy level is just nearer to the valency band and above the valency band. Above the valency band. Okay. Now see here. Now we are taking so density of holes in a valency band in case of in intrinsic semiconductor. This one. Now here density of ionized acceptors. Okay, that what is the density of ionized acceptor means? So Na is the concentration of acceptor atoms into F of E A. So F of E means probability of finding the hole. Okay, Na into F of E A gives the so density of ionized acceptor atoms. If you simplify this equation, Na into exponential of Ef minus Ef by Kt. So if you equate both means, so if you equate both and we can solve this equation, then we will get the Ef value. Then we will get the Ef value. Okay, so that is the first step. What is the first step means we have to equate these two equations. Okay, so from the those two equations, what we will get? Ef value we are calculating. Okay, this ef value we are substituting the so p value. So p is the density of holes in a p-type semiconductor. Sorry, intrinsic semiconductor. So that in that equation we are substituting the ef value. If you substitute means so if you substitute and you calculate means we can get the p value. We can get the so p value. So this is the density of holes in case of p-type semiconductors. Okay, otherwise carrier concentration of p-type semiconductor. Okay, next we discussed about the fermi level. Okay, so in that fermi level, yeah, with respect to the what is that concentration, with respect to the doping concentration or acceptor concentration also, fermi level will be changes. So previously we discussed about the with respect to the temperature. With respect to the temperature, what happened with increasing at lower temperature? That Fermi level is exactly middle. If you increase the temperature, just increase the temperature, what happened? That Fermi level is decreases. If you increase the further temperature, what happened? That Fermi level is increases and matches to the Fermi level of intrinsic semiconductor. Okay. Now, so according to based on the acceptor ions. So if acceptor concentration is acceptor concentration is very high means so that increasing of the Fermi level with respect to temperature is slower. If acceptor concentration is low means so increasing of Fermi level with temperature is very fastly. Okay, increasing of Fermi level with respect to the temperature is so very fastly. Okay, at a lower acceptor ions. Okay, this is about the Fermi level of intrinsic semiconductor. Okay, we will stop the lesson today. Then